Welcome back, everyone. Today, we get to the last unit of our course. For the next 3 weeks, we'll be talking about machine learning. And we'll start with a very popular method to build classifiers called naive Bayes. In this course, and up until now, we have been learning how to use a model to make optimal decisions. Action selection was based on search within our model. It was also based on reasoning and sometimes probabilistic reasoning. Now we're going to do something different. We're going to learn our model from the data we have, or in some cases from experiences that our agent initiates. And there are different kinds of machine learning because we can learn different things from this data. We can learn the parameters of the data. For example, if we have a Bayes net, how do we figure out the probabilities associated with it? We can also learn the structure of the Bayes net. Where are the arcs? Where are the dependencies? And finally, we can sometimes learn some hidden concepts from the data. We'll see this when we talk about clustering. Before we get started, I would like to share with you a tweet by Baron Schwartz. When you're fundraising, it's AI. When you're hiring, it's ML. When you're implementing, it's linear regression. When you're debugging, it's printf. It's a bit cynical, but maybe true. You'll be able to weigh in on this after we complete our unit on machine learning. So today we'll focus on a very popular technique called naive Bayes. Naive Bayes is a model-based classification technique. So we'll first try to understand the basics. What is classification? What model are we talking about? And what's so naive about it? We can think of classification as answering a multiple choice question. We are given some input, could be an image, could be some object, and we need to pick a class corresponding to that input. So for this image of a car, we need to pick one of the available answers. Is it a dog? Is it a car? Is it a box? Is it an alligator? We have a finite number of choices here. So here's a more formal description of a classification task. Given some input X, we have to predict a label or a class Y corresponding to X. A spam filter is an example of a classifier. Here the input is the email we receive in our inbox. The output is one of two options, spam or ham. So ham for some reason is a good legitimate email, whereas spam is an email that we do not want to read. So note that we only have two classes here. We call that a binary classification. OCR, or optical character recognition, is another example of classification. Here we have an image, which is a picture of the handwritten character. And our classifier has to predict the actual character. Is it an A? Is it a B? Or is it a digit? In our homework, we'll have a digit recognition classifier that will take as input handwritten images of digits, and the output here is one of 10 possible classes, 0 through 9. For medical diagnosis, our input consists of the symptoms or the test results, and our classes consist of the diseases that we're trying to diagnose. In the simplest cases where we're trying to detect the presence or absence of a disease, we have only two classes, and we also get a binary classifier. Automatic essay grading, believe it or not, is real, and it's also an example of a classifier. So the input here is actually a document, a text document, and the output is a grade. It could be A through F. So we would have 5 classes here. And finally, fraud detection is also a very common classification task. The input here is basically our account activity, and the classes are basically positive or negative. Is there fraud or is there no fraud? So here again, we have a binary classifier. And there are many more real commercial examples of classifiers. So classification is an important commercial technology. You don't have to be working at an AI company to be working on a classifier. Most commercial companies have real examples of classifiers that they're using. Let's take a closer look at spam detection. Our goal is to have some program that takes as input an email message. The program must be able to associate one of two labels, spam or ham, with the input email message. So how do we get there? We start by acquiring a large number of example emails. These emails must all be already labeled ham or spam. So someone had to read all these emails and label them for us. That's a lot of work. We assume that this has been done for us. To see what's involved, let's try to label these two emails. So the first one goes, Dear Sir, first I must solicit your confidence in this transaction. This is by virtue of its nature as being utterly confidential and top secret. So what do you think? Is this first email ham or spam? I vote for spam. I don't like this top secret in uppercase. And there is some transaction here and confidence. It just looks fishy to me. So I would say this is spam. Let's go on to the next one. Okay, I know this is blatantly OT, but I'm beginning to go insane. Had an old Dell Dimension XPS sitting in the corner and decided to put it to use. I know it was working pre being stuck in the corner, but when I plugged it in, hit the power, nothing happened. What about this email? I am tempted to say that this is a legit email, so I vote for ham. So as part of our setup here, we must have all this labeled data that someone manually labeled for us. And there's one more thing we need to keep in mind. Whoever labeled this data may have made a mistake. So these labels could contain errors. That's something that we should keep in mind. All right, so assuming we have this large collection of emails that somebody reliable labeled for us, now our goal is to learn to predict labels of new, future, unseen emails. That's what our spam classifier is supposed to do. So how did we decide that the first message was spam and the second one was ham? There were some clues in the message. There were some attributes of the message that pushed us in one direction or the other. We call these attributes the features. So here, I did not like the words top secret. There are usually some specific words in messages that raise a flag. There are also some patterns. Messages that contain dollar amounts or messages that are all or partially in all caps are more likely to be spam messages. Spelling errors usually signal spam, and it's not exactly because spammers do not know how to spell, but they try to fool the spam filter by misspelling suspicious words. And finally, there are also some non-text clues. For example, we can look at the sender of the message. If this is someone in our contacts, then it's likely that this message is ham, even if it's written in all caps, even if it contains spelling mistakes and dollar signs. It could just be a message from our friend who can't spell and who wants to sell us his old car. Now let's take a closer look at a digit recognition classifier. Here our input consists of an image of a handwritten character. This image may be represented by an array of pixel values. The output is a digit, 0 through 9. So here we don't have a binary classifier, we actually have 10 possible classes, 10 possible labels for each image. And here again, we start by acquiring a large number of images. These images must all be already labeled with a digit. Here again, someone had to look at these images and label them for us. So let's try to do that with the images here. The first one, I would say, is a 0. The second one is 1. The third one is a 2. The fourth one is a 1. For the fifth one, I'm really not sure. Is that a 2? Is that a 0? Who knows? So we see that this is not an easy task. It's easy to make a mistake here. Our goal is to learn to predict labels of new, future, unseen digit images. So what are our features here? We could use the intensity of the pixel for grayscale images, or to make things simpler, just a Boolean value for each pixel, describing whether that pixel is marked or not. We'll see later that using the pixel values alone as our features is tricky when we're dealing with images of different sizes, or with images that are tilted at different angles, like the two images of a 1 here, this one and this one. These two images do not have many pixels in common, and yet they both denote a 1. We may also use some shape patterns as our features. For example, how many loops are there in the image, and so on. Feature engineering in general requires domain knowledge. The goal is to create features that make sense for a very specific domain.